Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over how to find limits at removable discontinuities. Do not forget to visit our website at mathgotserved.com for access to a wide variety of math tutorials ranging from algebra to calculus. Let's take a look at question number 1. We're to find the limit as x approaches 0 of sine squared of 5x divided by 4x squared. Before we go ahead and evaluate this limit, let's go over a formula, a squeeze theorem formula that's going to help us. Okay, so remember that the limit as x approaches 0 of sine ax over bx is equal to a over b. All right, one of the variations of this formula that you see often is limit as x approaches 0 of sine x over x equals 1. In this case, a is 1 and b is 1. They're both identical, so you have a divided by a, which is equal to 1. All right, so let's go ahead and evaluate this limit. I want to be able to apply this formula to this situation. So what I will do is separate this limit and express it in the following format. Limit as x approaches 0 of sine 5x over x times sine 5x over x. Now there's a 4 down here. I can factor out the 4, so we have 1/4. Okay, so all I just did is I just expressed this square of the sine function as a product of factors. Okay, so sine 5x times sine 5x is sine square 5x. And then x times x is x squared on the bottom here. All right, so now I would like to go ahead and I want to make this, I can evaluate these two limits with this formula right here. We have the limit as x approaches 0 of sine ax over bx is a over b. So we have a 1 here and a 1 here. So let's go ahead and distribute this limit to these factors. This is one of the properties of limits. This problem now becomes 1 over 4 times the limit as x approaches 0 of sine 5x over 1 over 1x times the limit as x approaches 0 of sine 5x over 1x. Okay, so this limit simply becomes 5 over 1, and this one also becomes 5 over 1. So our limit is going to become 1 over 4 times 5 over 1 times 5 over 1. And when you multiply it across, your final answer will be 25 over 4. Okay? So that's that. All right, let's take a look at question 2. This involves radicals. So we will have to rationalize here. If we just evaluate this limit by direct substitution, we'll get an indeterminate form because we'll have a 0 in the denominator. Okay, so what we're going to do here is rationalize the numerator. So multiply the numerator by the square root of x minus 2 plus 1 over the square root of x minus 2 plus 1. So this is the conjugate. Okay, so if we distribute in the numerator, we will have the limit as x approaches 3 of x minus 2 minus 1 divided by, in the denominator, we'll have x minus 3 times the square root of x minus 2 plus 1. In the numerator, all I did is I took advantage of the difference of squares formula. If you have a minus b times a plus b, that's going to become a squared minus b squared. Okay, so when I square the square root of x minus 2, I have x minus 2. When I square 1, I'll have 1 there. Let's go ahead and simplify further. We'll have the limit as x approaches 3 of x minus 3 divided by the quantity x minus 3 times the square root of x minus 2 plus 1. Now these two are identical, so we can divide the numerator and the denominator by x minus 3. So we now have the limit as x approaches 3 of 1 over the square root of x minus 2 plus 1. Now we can evaluate this limit by direct substitution. We'll plug in 3. We'll have 1 over the square root of 3 minus 2 plus 1. This becomes 1 over this 3 minus 2 is 1, so the square root of 1 plus 1. That becomes 1 over 1 plus 1, which equals to 1 over 2. All right, let's take a look at question number 3. We are to find the limit as x approaches 0 of 1 minus cosine 2x divided by cosine 4x minus 1. Before we evaluate this limit, first of all, let's go over an identity that I'll be using here, which is the double angle identity for cosine. Okay, so cosine 2 alpha is equal to 2 cosine square alpha minus 1. All right, we can apply that situation to the denominator here. If we have cosine 2 times 2 alpha, okay, applying the formula above here, this becomes 2 cosine square 2 alpha minus 1. The same thing, the only difference is that the double angle is doubled here, and then there I just have the double angle directly. Okay? All right, now let's take a look at this limit. As indicated earlier, you can apply the double angle identity for cosine to this term here, cosine 4x. Let me write it in a way that makes it obvious. So we have the limit as x approaches 0 of 1 minus cosine 2x. Now that divided by cosine 2 times 2x minus 1. All right, so let's apply the double angle identity to the denominator. Think about alpha as 2x here, so this could be alpha. Our limit now becomes the limit as x approaches 0 of 1 minus cosine 2x divided by, now in the denominator you're going to have 2 cosine squared 2x minus 1. Okay, let's go ahead and write that down. So it's going to be 2 cosine square 2x. Imagine as though 2x is your alpha. Okay, so you have 2 cosine square alpha minus 1, but alpha is 2x, so that's why we have it here. All right, so it's minus 1, and there was a minus 1 there before, so let's introduce that. We introduced that. Minus 1, minus 1. So this now becomes the limit as x approaches 0 of 1 minus cosine 2x divided by 2 cosine square 2x minus 2. All right. Now let's go ahead and factor out the 2 from the denominators. I can pull it out and express it as 1/2 of the limit as x approaches 0 of 1 minus cosine 2x divided by cosine square 2x minus 1. Okay, now in the denominator I have a difference of squares, so I can factor that using my difference of squares formula. So I have 1/2 times the limit as x approaches 0 of 1 minus cosine 2x divided by the factored form of my denominator becomes cosine 2x minus 1 times cosine 2x plus 1. Okay, imagine a squared minus b squared factors into a plus b times a minus b. So that's what we have here. Now if you notice, these two, the order is reversed. So if I divide these two, I'm going to end up with -1 on the top. All right, let me rewrite it in another way so it's all, you can really see what I am doing. So we have 1/2 times the limit as x approaches 0 of negative parenthesis cosine 2x minus 1. So I reverse the order in the numerator so you can match one of the factors in the denominator. So I'll have in the denominator cosine 2x minus 1 times cosine 2x plus 1. Now these two are identical, so I can factor them out. These two cancel out. Our limit becomes the limit, 1/2, the limit as x approaches 0 of -1 over cosine 2x plus 1. Now I can evaluate this limit by direct substitution. Let's go ahead and do that. We'll have 1/2 times -1 divided by the denominator evaluated at x equals 0. So we have cosine 2 times 0, 2 times 0 plus 1. That becomes 1/2 times -1 over cosine 2 times 0 is 0. Cosine 0 is 1. So we have 1 plus 1. And then we have 1/2 times -1/2. And your final answer is -1 over 4. All right, so there goes your limit. All right, let's take a look at question number 4. So for problem 4, we are finding the limit of a rational expression. Limit as x approaches 0 to of x divided by 1 over -2 plus x plus 1 over 2. All right, so what I'm going to do here is I want to get rid of the denominator in the denominator. So I'll simply multiply all the numerator and the denominator by the LCD of the denominator. Okay, so the LCD of these two, let's write that on the side. The LCD of -2 plus x and and 2 is the product of both of them, 2 times -2 plus x. That's the LCD. Okay, so what am I going to do? I'm going to multiply every single term by that LCD so I can get rid of the denominator in the denominator. Okay, so we have limit as x approaches 2 of x divided by, now we have 1 over -2 plus x plus 1 over 2. Let me just introduce one more step. So I'm multiplying the denominator by the LCD, which is 2 times -2 plus x. And I also have to multiply the numerator by the same value so I don't change the problem. Okay? So I multiply it in that fashion. Now I will have the limit as x approaches 2 of x times, let's put it 2x times, reverse the order here, x minus 2. That's for the numerator after distributing this. After just expressing them as factors, I did not distribute. And then downstairs here, what do I have? I'll have, now if I distribute this term to this, the negative 2 plus x will cancel out, so I'll be left with 2. Plus, now if I distribute 2 times negative 2 plus x with the 1/2, the 2's cancel out, so I'll be left with negative 2 plus x. Let's simplify that. We have the limit as x approaches 2 of 2x times x minus 2 divided by now if I simplify the denominator, you notice that these 2's cancel out. Plus 2 plus minus 2 is just 2 minus 2, which is 0. And I'm left with an x. These two x's divide out. My limit becomes the limit as x approaches 2 of 2 times x minus 2. Now I can simplify this by direct substitution, evaluate this limit by direct substitution. So I'll have 2 times 2 minus 2, which is 2 times 0. Our final answer is going to be 0. All right? So that's the limit. All right, let's take a look at question number 5. Now for number 5, it's clear that if I plug in 3 into the denominator, I'll have an indeterminate form. We will be dividing by 0, which is not acceptable. So how about we factor the numerator to see if we have a removable discontinuity at x equals 3. Okay? So let's factor the numerator using the x game. AC is 6, b is negative 5. The two numbers that work. Let's try 2 and 3. Minus 2 minus 3, add to give you the bottom, and then multiply to give you the top. Okay, so we have the limit as x approaches 3 of negative quantity x minus 2 times x minus 3 divided by x minus 3. Now what you notice happening here is that x minus 3, these two factors can cancel out, hence 3 is a removable discontinuity. The limit now becomes the limit as x approaches 3 of negative x minus 2. Now this limit can be evaluated using direct substitution. Alright, so let's go ahead and evaluate this. So we'll have negative 3 minus 2, which equals negative 1. So that's your final answer. Now let's take a look at question 6. This one is a function that is piecewise. We have a piecewise defined function in this situation. We are finding the limit as x approaches 0. So as x approaches 0, we know that we're never having x equals 0. We're simply approaching 0 from both sides. Okay, so we have a situation here that let's illustrate with a number line approaching 0 from both sides. So when you're on the 0, actually when you're on 0, what's active is negative 5. If you're not on 0, you're going to be using the function negative 3 plus x minus 2 to the left of 0. That's you're approaching 0 from the left. If you're approaching 0 from, this is 0 right here, 0 from the right, you're still going to use the function negative 3 plus x minus 2. Okay? So that's what we're going to be using. So the limit as x approaches 0 of the function, this is a double-sided limit, is equal to the limit as x approaches 0 of negative 3 plus x minus 2. This limit can be evaluated by direct substitution. So we have negative 3 plus 0 over 2. If we go ahead and evaluate that limit, we're going to end up with negative 3. All right? So that's your answer. Now you can go ahead and try out some practice problems to ensure that you've mastered the concepts covered in this tutorial. Thanks so much for taking the time to watch this presentation. We really appreciate it. Feel free to subscribe to our channel for updates to other cool tutorials such as this. Do post a comment in the comment section to let us know what you think about this clip, or if you want to make requests for other tutorials to aid you in mastering calculus. Thanks again for watching. Have a wonderful day.